Hi, this is Kylie, Cerise, and Tito, and we are Team A1, Cooperative versus Non-Cooperative Autonomous Driving. Autonomous driving will likely be the future framework of transportation. It's currently revolutionizing the industry by being the forefront of much research. Our team has decided to explore new improvements to the current system by comparing the effects between cooperative and non-cooperative autonomous driving. Currently in autonomous driving, vehicles make decisions based off of their immediate surroundings to optimize their individual goals. This is called egocentric driving or non-cooperative driving. Vehicles currently do this by having individual sensors that can sense immediate obstacles in their environment. In our project, we will simulate this by having vehicles make decisions based on what's in front of them. On the other hand, cooperative driving is when all the vehicles in the system are communicating with one another to make a collective decision to optimize the overall system's goals. It extends all the vehicle's sensory range by sharing more information to one another, including the vehicle's intended path. By allowing vehicles to make informed decisions, we believe this will improve safety and overall traffic flow. Our solution was to create a software-based simulation to experiment with different scenarios of cars moving in circles on a figure-8 track. Performance would be measured by comparing throughput between the two approaches. We define throughput as the number of vehicles that pass through the intersection over a given period of time. After reading related papers, we set a goal to achieve at least a 30% increase in throughput between the cooperative and non-cooperative cases. For demo purposes, we decided to design a customizable setup that would allow us to create and visualize different scenarios. For testing purposes, we also incorporated a mode that would create predefined scenarios, simulate them using both approaches, and generate metrics for us to compare. The interactive mode uses the mouse and keyboard to control the simulation. This is the starting screen, and the user can click where on the track they want to insert a vehicle. Once you insert a vehicle, you can visualize its information on the top left. The timer and throughput are shown on the top, along with the mode that the vehicles will be operating under. There are different mode buttons on the top right. The detection radius visualizes where the vehicles are getting information, and the mode button changes the behavior of the cars. To start and stop the vehicles, the user presses the S button on the keyboard. To reset the setup, the user presses the R button on the keyboard. The user can also increase and decrease the speed of all vehicles by selecting 1 and 2 buttons respectively. To compare metrics, we created a testing mode that turned off the simulation graphics and decoupled the internal simulation time from system time. This allows the testing to run much faster. We randomly generated 50 test cases and for each test included 9 to 13 vehicles and let the vehicles run for 40 seconds. In addition to throughput, we recorded average velocity, average acceleration and deceleration, the frequency of each vehicle accelerating and decelerating, and the average waiting time for each vehicle, which is the time when a vehicle's velocity is 0. The main driving model used was the Intelligent Driver Model, or IDM. This model defined a set of equations and relationships between key parameters that characterized how the vehicle moves. Using the distance to the nearest obstacle, the difference in velocities, and other constants we defined such as optimal velocity, maximum acceleration, etc., the IDM was able to compute an acceleration value for the vehicle such that it would safely react to any surrounding obstacles. This driver model was used for both the non-cooperative and the cooperative cases. In the cooperative approach, as vehicles approach/move within the intersection, they communicate the length of the queue to each other. Priority is assigned to lanes based on a weighted combination of features which prioritizes lanes with longer queues and a closer frontmost vehicle. Multiple vehicles are allowed past the intersection from one lane to reduce the delays from the frequent stopping and starting of the vehicles queued up at the intersection. There's a limit on the number of vehicles that can pass from one lane, and that's to prevent starvation. Cars form chains, as the leading vehicle in the chain can communicate its intended path and acceleration to all the other vehicles in the chain, allowing them to move similarly to the lead vehicle. This allows for a much closer following distance in this approach. Here we demonstrate an example of cooperative autonomous driving in dense tracks. We start by showing how the non-cooperative case works. In this approach, each vehicle acts independently. Therefore, the vehicles take turns one by one passing through the intersection. In the simulation, we can first examine the left track since there are more vehicles in it. We will notice that as the first vehicle, ID 6, passes through the intersection, the rest of the vehicles in the left track move slowly to approach the intersection and fill in the gap that vehicle 6 left. However, because each vehicle is acting independently, it must wait until there's a large enough buffer distance between itself and the obstacle in front of it before it can start moving forward. As you can see, this prevents the last few vehicles in the left track from advancing immediately because the delay is propagated through each vehicle in the chain. In other words, vehicle 8 must wait for vehicle 7 to move far enough before it can proceed. Vehicle 9 must wait for vehicle 8, and etc. This becomes an issue in this scenario because when vehicle 6 approaches the last vehicle on the left track, it's still blocking the intersection. Thus, as the vehicle from the right track tries to pass through the intersection now, it must wait until vehicle 6 has fully entered the left track before it can continue. In the cooperative case, the first thing we will see is that now 3 cars pass through the intersection at a time. This is because, as mentioned earlier, the communication allows the vehicles to coordinate and let multiple vehicles pass through while maintaining fairness. This eliminates a lot of the frequent start-stop behavior from vehicles when they're forced to alternate. The next important aspect in the cooperative case is chaining. We can treat all the vehicles in the left track as if they're in a chain because they're all very close together. In the code, we define some maximum separation threshold for this. Chaining allows vehicles to follow each other at a much closer distance due to the extra information provided through communication. Not only do the vehicles know the position and velocity of the vehicle or obstacle in front of it, now they also know its acceleration and whether it plans to accelerate or decelerate. Therefore, vehicles can now much more closely follow the next vehicle, and in the case where the lead vehicle must abruptly stop if it sees an obstacle, all vehicles in the chain can instantly set their deceleration to the same value as the lead vehicle to prevent collision. This can all be achieved through the advantages of communication in the cooperative approach. A much closer following distance will now allow the last few vehicles in the left track's chain to immediately move forward and fill any gaps that the vehicles passing through the intersection create. This means that the left vehicles passing the intersection can clear the intersection and move completely into the left track by the time the right vehicle needs to pass through, removing any blockage there. Here we present the two implementations shown side by side to illustrate the differences. In the non-cooperative case, the small delays that prevent right vehicles from passing through the intersection get cascaded over all the loops, whereas the cooperative case runs smoothly and more efficiently. Overall, we see that the non-cooperative case achieves only 44 loops during the 40 seconds it was running, while the cooperative case does much better with 65 total loops. This scenario does a great job in displaying the advantages of both allowing multiple vehicles to pass through the intersection and also chaining. As you can see in the results, we reached a 30.33% increase, which satisfies our requirement. There's also a decrease in waiting time, which is as expected since the cooperative mode improves traffic flow, lowering the amount of time each vehicle has to wait. Chaining removes the intermediate delays between vehicles in a chain and allows multiple vehicles to pass the intersection at a time. We expected to see a decrease in average acceleration and deceleration in the cooperative case because we believe that lower values attributed to an increase in the efficiency of the system. However, in our results, we observed an increase in these metrics. We deduced that in the cooperative case, vehicles hit the optimal velocity much more often, and therefore the values for acceleration and deceleration were much higher due to the higher change in velocity over time. We tested this theory by adding a new metric, which was measuring the frequency in which vehicles accelerate and decelerate in the system. We observed that in the cooperative case, it yielded lower values for this metric in both acceleration and deceleration, meaning that vehicles did not have to speed up or slow down as often when they communicate. This supported our theory of an increased efficiency in the system in the cooperative approach. There are still a lot of unknowns in this field of research. How would the approaches compare in different tracks other than the figure 8? Can communication between vehicles also improve the safety and reliability of autonomous vehicles? How would this scale to the real world? Would all vehicles on the road need to be autonomous? Would there need to be a global server on the side of the road that collects the information and makes decisions for the system? Our project has only scratched the surface of the potential research in this field. There's still a lot that can be done. However, We have shown significant advantages in performance when vehicles are able to communicate important information about their decisions. Our results highlight the benefits of pursuing further research in this field, and we hope to see more progress as autonomous vehicles begin to integrate with our daily lives.